We've all heard the undisputed fact, right? For as long as most of us can remember, we've been told that the blue whale is the absolute heavyweight champion of our planet's history. We picture them gliding through the oceans, dwarfing submarines, completely unmatched. Nothing on land or sea has ever come close, or so the story goes. But what if the fossil record is hiding a completely different truth? What if the ground beneath our feet once shook with the weight of an animal that could look a blue whale right in the eye and actually match it, pound for pound?
170 tons. Just let that massive number sink in for a second. To really put that into perspective, we're talking about the combined weight of 30 adult African elephants. Or picture a line of 10 fully loaded semi-trucks parked end to end. That staggering figure is the upper weight estimate for a lost prehistoric giant, an absolute titan that challenges literally everything we thought we knew about the biological limits of life on land.
Welcome to This Explainer, the ultimate heavyweight champion. We're going to completely unpack the awe-inspiring science behind the largest land animals to ever walk the earth. Get ready for a prehistoric detective story that weaves together fragmentary bones, cutting-edge math, and the crazy biological engineering that made these walking mountains possible.
The ultimate heavyweight champion. To truly understand the breathtaking scale of the biggest dinosaurs, the super sauropods, we first have to see how they stack up against modern giants. A blue whale can expand up to an incredible 30 meters long, but when you look at extinct sauropods, their unbelievable length, driven by those sweeping whip-like necks and tails, allows them to occupy almost the exact same spatial footprint. But length is just one dimension, right? Mass is a whole different ballgame.
Which brings us to Section 2, how to weigh a dinosaur. Obviously, you can't just wrangle a dinosaur onto a scale. So scientists have fiercely debated how to weigh them, leading to a massive clash in paleontology, volumetric modeling versus limb bone scaling. Limb bone scaling looks at the circumference of the leg bones and estimates weight based on modern mammals. But, spoiler alert, this drastically overestimates weight for sauropods, because they evolved unusually robust, pillar-like legs. Volumetric modeling, on the other hand, creates rigorous, high-fidelity 3D anatomical blueprints to calculate tissue volume. It's proven to be way more accurate.
And volumetric modeling relies heavily on mapping out the precise dimensions of core trunk elements. We're talking massive spine bones, like the dorsal vertebrae and sacrums. By mapping these out in 3 dimensions, scientists can accurately reconstruct the dinosaur's massive torso. Because think about it, that central trunk is where the vast majority of the animal's enormous weight was actually stored. It's literally the most critical piece of the puzzle.
Section 3, the Titanosaur contenders. Now that we have our methodology locked in, let's meet the heavyweights we actually have good skeletons for. You might have seen flashy headlines recently hyping up a dinosaur called Patagotitan as the biggest ever discovered, weighing around 52 tons. But when researchers applied strict volumetric models to both Patagotitan and the older favorite, Argentinosaurus, the data told a totally different story. Argentinosaurus had a main back section that was about 1/5 longer than Patagotitan's. The models definitively proved that Argentinosaurus was significantly larger, weighing in at a staggering 70 tons. Honestly, it wasn't even close.
And a lot of that weight comes down to their shape. Titanosaurs, like Argentinosaurus, were uniquely built with incredibly broad pelvis and abdomens. They weren't just long, they were incredibly wide. This massive, barrel-like gut maximized their overall mass compared to narrower sauropods, basically acting as a giant fermentation tank for their plant-based diet. So, Argentinosaurus is the largest dinosaur known from substantial remains, but notice I said substantial remains.
Section 4, the ghost of Brouhathkaisaurus. Get ready because here is the major twist of this explainer. What if there was a dinosaur that made the 70-ton Argentinosaurus look totally modest by comparison? In the late 1980s, fragmentary but utterly massive remains were discovered in the late Cretaceous rocks of India. Tragically, these fossils were so incredibly fragile that they disintegrated before they could be preserved in a museum. A totally heartbreaking loss for science. But before they crumbled, researchers extensively documented them, identifying a colossal tibia, the lower leg bone. Based on their measurements, this singular tibia was roughly 29% larger than the equivalent bone in the already gigantic Argentinosaurus.
So, scaling up from Argentinosaurus to match the sheer size of that Brouhathkaisaurus tibia gives us a jaw-dropping calculation. A conservative estimate places it right in the middle at 120 tons, with a plausible range between 110 and 130 tons. Put that monumental number in perspective. This places a fully terrestrial, land-walking animal squarely in the weight class of a fully grown female blue whale. The idea of something that heavy walking on dry land is just almost incomprehensible.
Now, a quick touch on the math, because scientific accuracy absolutely matters here. Scientists noted that in sauropods, tibia-to-femur ratios scale with a biological rule we call negative allometry. Simply put, as these animals get bigger, the thigh bone doesn't lengthen quite as fast as the shin bone. This means Brachiosaurus probably had slightly more slender upper legs than a direct 1-to-1 scale-up would suggest. That's exactly why scientists favor the 120-ton estimate rather than that absolute mathematical maximum of 170 tons. Either way, mind-bogglingly huge.
Section 5. The biology of gigantism. Which brings us to a huge question. How did they actually exist? Surviving at this unprecedented size in standard Earth gravity required an absolute biological masterclass. To reach blue whale sizes on land, sauropods evolved a highly specialized evolutionary toolkit. It all started with their heads. By evolving tiny, lightweight heads lacking heavy chewing muscles, they drastically reduced weight at the end of their spine. This meant they could afford to grow ridiculously long, weight-saving necks, sometimes stretching up to 15 meters long, sweeping back and forth like a giant construction crane.
Those incredibly long necks dictated a brilliantly efficient feeding strategy. Imagine weighing 100 tons. You absolutely do not want to waste precious energy walking around. So first, park in one spot. Second, sweep that crane-like neck up, down, and side to side across the canopy. And third, strip the trees bare like a giant corn on the cob. They swallow their food completely whole, consuming upwards of 45 kilograms of plants daily without burning vital calories to take a single step.
But here's their real secret weapon for getting massive. To support that giant body, they couldn't have solid, dense bones. Instead, sauropods evolved a highly pneumatized, honeycomb-like skeleton. Their vertebrae were filled with intricate air sacs deeply connected to their respiratory system. In some extraordinary cases, their spine bones were literally 60% air. This drastically slashed their overall weight while acting like a modern bird's lung, pumping oxygen through their colossal bodies in a continuous, highly efficient one-way flow.
Operating at this immense scale on land also generates a terrifying amount of internal body heat. Without water to cool them down like a whale, they needed a way to stop from literally boiling from the inside out. Well, their 15-meter necks, combined with that complex air sac system, essentially acted as giant biological radiators. They had a high metabolism, but their long necks provided the immense surface area needed to effectively bleed off all that excess internal heat.
Section 6. Land Titans versus Sea Giants.
Let's bring this explainer full circle and look at the big picture. It's a tale of two vastly different evolutionary timelines. Sauropods completely dominated the Earth, maintaining massive 50 to 100-ton body sizes continuously for a staggering 100 million years. Whales, on the other hand, are latecomers to the heavyweight division. They only achieved their giant 100-plus-ton sizes very recently, just in the last few million years, largely driven by unique oceanic conditions from recent ice ages.
And that leaves us with a thrilling realization about the limits of discovery. Paleontologists suggest that the known upper size limit has a huge probability of expanding as we find more fossils. Think about it. We have a massive sample size of modern blue whales swimming in our oceans right now, but our sample size of fossilized Titanosaurus is incredibly tiny in comparison. Because complete fossils of these behemoths are so exceptionally rare, it is statistically highly unlikely we've actually found the absolute largest individual to ever live. The true maximum size of sauropods is almost certainly still buried in the rock.
Which leads us here. The ghost of Brachiosaurus proves that the limits of biology on Earth are far wilder and far heavier than we ever imagined. If an animal the size of a blue whale could walk across the ancient Indian subcontinent, what other colossal giants are still waiting out there, hidden beneath the Earth, ready to rewrite our history of life all over again? Thanks for joining me for this explainer. Keep asking questions and keep exploring.